maxima and minima, and to confirm the maxima points and minima points and to find maxima value and minima value, we have different derivative tests, second derivative test, nth derivative test. Okay, see, from the discussion one thing is very clear. What is that? If we have a graph like this with an upper peak, at this particular point derivative is 0. See, for suppose if you say this particular point is p, then dy by dx at p is equals to 0. As well, second derivative d square y by dx square at this particular point p is less than 0, and so it indicates the maxima point and it gives us maxima value. Okay, it's an upper peak. Why this second derivative is less than 0 and why this first derivative is 0, and we discussed everything. Okay, we discussed the reasons and the answers for these two questions in our previous classes. In the same way, for suppose if you have a lower peak at a point p like this, then at this particular point, or you may say another point like some q, and at this point dy by dx at q is again 0. As well, second derivative d square y by dx square at q is greater than 0, and I explained you why this d square y by dx square at q is greater than 0. It is just because of the slope of the tangents at different points in the neighborhood of q. Already we discussed it in our previous class. Okay, see, we know this. Okay, we know about this upper peak, we know about this lower peak, we know about the maximum minimum points which we learned in our previous class. And now in this class I am going to discuss you about the curvature of the function. Okay, curvature of the graph of a function and sign of the curvature. See, curvature in the sense, see, usually we know about concave and convex. See, here we use only one word, concave. Concave upward as well concave downwards. See, first suppose if you have a function like this, then this type of function usually called as concave upward, whereas if you have a function like this is called usually concave downward. Okay, see, discussing about this concave nature of a function is considered as its curvature. Curvature of a function is simply nothing but discussing concavity or as well convexity of the graph of a function is considered as curvature. Okay, you just you just memorize these two, and I will use these two in mentioning different ideas of this curvature. Okay, see, once if you observe, see, you just look at this part of the graph. This part of the graph is just like concave upwards, and this part of the graph is also just looking like concave upwards, whereas this part of the graph is looking like concave downwards, and this part is again looking like concave downwards. Is it right? Okay, I will give you when we say the graph of a function is concave upward, when there is a chance to say the graph of the function is concave downward, I will give you. Okay, first of all, what I am going to tell you is, you just have a look. See, when the graph or the curve bends above its tangent at a point, okay, if curve bends above its tangent, at a p, what will happen? If curve bends above its tangent at a p, if the curve bends above its tangent at p, then the curve is mentioned as concave upwards or concave downwards. Usually we use this particular word, concave upwards. Okay, we don't use the convex word. We always use concave upwards as well concave downwards. Okay, this shape of the curve is considered as concave upwards as well convex downwards. So you just memorize this particular word. What is concave upwards? Concave upwards is just look like a cup shape. Okay, see, if you have a bowl which holds water, it is of this shape, right? And it is considered as concave upwards. So when we say the curve is concave upwards, if curve bends above its tangent at p, See, at a particular point P, if this is the tangent for the curve is bending above its tangent. If this is the tangent at this particular point P, then the curve is bending above its tangent. Okay, right. So, at this particular point P, for this curve if you calculate, since the curve is increasing, right? Since the curve is increasing, dy by dx is greater than 0. Whereas here, the curve is decreasing. Always we will change x values from left to right. Always we will raise the values of x. According to the change in x, what you say about the graph? The graph is decreasing, and so here dy by dx is less than 0. Okay? And the next thing, here at this particular point P, the curvature, see, d square y by dx square is greater than 0, and for this again, d square y by dx square is greater than 0. So we say that the sign of the curvature is positive. Sign of curvature is simply nothing but sign of this d square y by dx square. See, when you combine these two graphs together, when you combine these two shapes together, okay, if you combine these two shapes together, they will form a lower peak graph. At this particular lower peak, already we know that d square y by dx square is positive, and that's why, see, for this part d square y by dx square is positive, for this part d square y by dx square is positive. So if at a particular point P, for a function f, first derivative is greater than 0, second derivative is again greater than 0, then this is the shape of the graph in the neighborhood of P. And again at a particular point, if first derivative is less than 0 and second derivative is greater than 0, then this is the shape of the graph in the neighborhood of that particular point. Is it clear? See, this is, you may take it as A, if the curve bends above its tangent at P. In the same way, there is a chance to write concave downward shape. Okay, so and you just have a screenshot for this bit A, then I will give you bit B. It relates to the shape of the graph which is concave downwards. Okay, simply the opposite one. For suppose if you going to take B, if the curve bends below its tangent P, then the curve is mentioned as concave downwards and convex upwards in the neighborhood of P. And here sign of curvature is negative for this time. And what will be the shape? Okay, see, if you look at the shape, yeah, I will give you. The shape of the graph will be like this. This is the tangent and the curve is bending below its tangent. Okay, and if this is the tangent and the curve is bending below its tangent. Okay, so these are the possibilities for concave downward shape. Okay, concave downwards, or you may call it as convex upwards. Usually we will concentrate on this particular word. What is concave downwards, and previous shape is concave upwards. Again, for this graph, if you observe, what you will observe, see here the graph is continuously increasing, whereas this graph is continuously decreasing. Always we will think from left to right. When you move from left to right, the graph is decreasing. When you move from left to right, the graph is increasing. Since the graph is increasing here we say that dy by dx greater than 0, and here dy by dx less than 0. And again, when you combine these two shapes, it is looking like an upper peak. At that upper peak, already we know that the second derivative is negative. So d square y by dx square is less than 0 here, as well d square y by dx square is less than 0 here. So at a point for a function, if the first derivative is positive and second derivative is negative, then the shape of that graph in the neighborhood of that point is in this shape, and this is the shape of the graph in the neighborhood of a point if first derivative at a point is negative, as well second derivative at a point is also negative. Totally we have 4 different shapes. Okay, this is one shape. Okay, and again this is another part, this is another part, and this is another part. Okay, we see these 4 shapes we need to decide depending on the first derivative value as well second derivative value at a point for a function. Is it clear? Okay, if first derivative is positive, it represents increasing function. See, this is increasing function, as well this is also increasing function. And if first derivative is negative, this is decreasing, as well this is also decreasing. Any one of these two will happen depending upon first derivative. Okay, and when you think about second derivative, If second derivative is positive, then if second derivative is positive, then it is what? Concave upwards. Concave upwards means these two shapes, and if second derivative is negative, concave downwards means these two shapes. Depending upon four values, okay, two values, dy by dx and d square y by dx square, we need to decide the shape of the graph among these four. Okay, have a look. This is something about the curvature. Depending on this curvature or concavity of a graph, next we will define about the point of inflection for a graph. Okay, so first of all have a look, and then I will discuss about point of inflection. Okay, make a note, go with a screenshot. So finally, to decide the curvature of a function, this is the process. See, if we have a function y is equals to f of x, and we are going to check the concavity or curvature of this function at a point P, first of all calculate dy by dx at P. And if you calculate the derivative at P, that derivative value may be greater than 0, may be less than 0, and maybe is equals to 0. If derivative is positive, then we say that the function is increasing. If derivative is negative, the function is decreasing. Whereas if derivative, first derivative is 0, we say that the function is almost constant at that point, and that point is considered as what? Critical points. Okay? And if the derivative is less than 0, the function is decreasing, then the graph may be any one of these two possibilities. If the function is increasing, the graph may be any one of these two possibilities. Now we need to decide which one is correct for the given function, and we need to decide which one is correct for the given function. Then in that case we need to think about second derivative, d square y by dx square at P. If that second derivative at P is positive, this is the graph. If second derivative at P is negative, this is the correct graph for the function at the point. In the same way we will check here. See, if the second derivative at the point is greater than 0 along with this first derivative, this is the graph, and in the second case this is the graph. Based on this dy by dx at P value as well as d square y by dx square at P value, we will decide the curvature of the given function in the neighborhood of the given point among these four possibilities. That's what I am saying. Okay, have a look. Go for a screenshot. Next thing is points of inflection. We already learnt about critical points, and now this is something about points of inflection. See, points at which curve changes its concavity or curvature are considered as points of inflection. Discussing and analyzing about the curvature of a graph as well as points of inflection for a graph helps us a lot in sketching the shapes of the graphs actually. And now we are analyzing through graphs. At the end we will use this concept to sketch the graphs. Okay, see, point at which curve changes its concavity. So we learnt about two different curvatures of the graph, concave upwards as well concave downwards. For suppose if the graph shape is like this, see, almost at a particular point here, see, this is concave upwards and this is concave downwards. So at this particular point, the curve is changing its concavity. So these points are considered as points of inflection. Okay, for suppose if I have a graph like this, you just have a look. See, this is concave upwards, and after this particular point the graph is becoming concave downwards, and again after this particular point the graph is what? Concave downwards here, and this is what? Concave upwards. You just have a look. Okay, here the shape of the graph is concave upwards, here the shape of the graph is concave downwards, and here the shape of the graph is concave downwards, and here the shape of the graph is concave upwards. And now when you observe at this particular point, curve is changing its concavity from concave upwards to concave downwards, and at this particular point the curve is not changing its concavity, right? Because concave downwards as well concave downwards. So this is not a points of inflection. And again at this particular point concave downwards to concave upwards. So this is a point of inflection. This is a point of inflection, but this point is not a point of inflection. Why? Because here the curvature is not changing. Okay. Not only this, sometimes we may face the graphs like this. So here the curve is concave upwards and here the curve is concave downwards. So again we consider this point as a point of inflection. When you observe this total picture, a point is considered as concave. See, a point is considered as point of inflection. In the neighborhood of that point, what happens? The concavity of the function changes. Okay, what I am going to tell you is, if a point, some x naught, is point of inflection, if x naught is point of inflection, you just mark everything as AB. Okay, so first of all, this is bit A and this is B. If x naught is point of inflection, then concavity of f of x in the neighborhood of x naught changes. See, concavity is changing in the sense, the second derivative usually represents the concave nature of a graph, so that implies second derivative, okay, d square y by dx square changes its sign in the neighborhood of x naught. You just have it. So we call a point as the point of inflection. Okay, when, because it is changing its concavity, that in turn represents that second derivative is changes its sign in the neighborhood of x naught, then those points are considered as points of inflection. Since second derivative is changing its sign, then what happens exactly at that x naught? If you look exactly at that x naught, second derivative will become 0 or not exist. I will give you point C. Okay, so the next thing is, if x naught is point of inflection, then what will happen? Then second derivative f double dash of x naught is equals to 0 or f double dash of x naught not exist. Okay, either 0 or not exist. Okay, you just have a look. What I am going to tell you is, if x naught is a point of inflection, exactly at that x naught second derivative is either 0 or not exist, and in the neighborhood of x naught, if you check second derivative, it changes its sign. Okay, if in the left side of x naught second derivative is positive, then in the right side of x naught second derivative will be negative. If in the left side of x naught second derivative is negative, then in the right side of x naught second derivative is positive. It changes its sign, and but exactly at x naught the second derivative value is 0. So to find the point of inflection, usually we use this particular idea. Okay, to find the point of inflection, first of all we use this idea to find x naught, and then we will check whether it is changing its sign or not in the neighborhood of x naught. Okay, you just have a look. So at the end, this is something about the points of inflection, and these points of inflection are also termed as sometimes, okay, these points of inflection are sometimes also considered as hypercritical points. Already we know about critical points, right? At critical points first derivative is 0. Okay, but what you say about hypercritical points? At this hypercritical points second derivative is 0. Okay, right? We call it as hypercritical points or second order critical points. Just have a look. At the end, this point of inflection is also called as hypercritical points or second order critical points, and at these points of inflection second derivative is either 0 or not exist, and these points of inflection helps us in analyzing the curvature of the functions at different points. Okay, have a look. So the next thing is finding points of inflection. Okay, I have some simple examples to discuss about points of inflection. Okay, for example, first thing is f of x is equals to x cube. We need to find out point of inflection for this f of x is equals to x cube. As I said, first of all you need to calculate first derivative. F dash of x is equals to 3x square. Okay, f dash of x is equals to 3x square, and what you say about f double dash of x? F double dash of x is equals to 6x. Okay, For points of inflection, we need to equalize this second derivative to 0. Okay? Yeah. Okay. For inflection points, what we need to do? We need to do that f dash of x is equals to 0. Since f dash of x is equals to 0, you will get that x is equals to 0. So at x is equals to 0, we have a points of inflection. Again, if you use this x is equals to 0 for this f dash for first derivative is also 0 at this point. First derivative is 0 as well, second derivative is also 0. Okay, so usually we say that if first derivative is 0, we say that there exists an horizontal tangent at the point. Okay, if second derivative is 0, there is a point of inflection, and we need to check in the neighborhood of x. What I am going to tell you is x less than 0 and x greater than 0. X less than 0. So in the left side of x, if you check second derivative, since x less than 0, second derivative is also less than 0. Here f double dash of x is less than 0 and x greater than 0. For x greater than 0, if you check f double dash of x is again greater than 0. Okay, see 0 is the point of inflection now. Why? Because it is changing its sign in the neighborhood of 0. First of all, we are going to find hypercritical points. See where f double dash of x is 0. See, sometimes hypercritical point may not be a inflection point also. So for that we need to check whether it is changing its sign or not. Always it happens usually. Okay. So this is a second order critical point. At that point, if you observe, second derivative is changing its sign. So that 0 is the point of inflection. If you wish to sketch the graph at that particular point, okay, see less than 0. Less than 0 means concave downwards. Greater than 0 means concave upwards. So this is the rough sketch of the graph for f of x is equals to x cube. Okay, as I said, at this point 0, first derivative is 0. That means if first derivative is 0, that represents a horizontal tangent for the graph. So at this point 0, horizontal tangent is x-axis. This x-axis acts like a tangent for this graph also. This is another interesting observation related to the inflection points. At inflection points, if you sketch the tangent for sure intersects the curve. Tangents at inflection points for sure intersects the curves. Okay, you just note that particular point also. Okay, so now 0 is the point of inflection for this f of x is equals to x cube, and this is the rough sketch of the graph. Have a look and then I will discuss f of x is equals to x power 1 by 3. Okay, so this is the graph. And now f of x is equals to x power 1 by 3. For this you just calculate f dash of x. F dash of x is equals to 1 by 3 into x power 1 by 3 minus 1. Okay. So x power 1 by 3 minus 1 means what? Okay. Yeah. Minus 2 by 3. So that is equals to 1 by 3 into x power 2 by 3. That is f dash of x. Then what to say about f double dash of x? F double dash of x is equals to 1 by 3 into, since it is x power minus 2 by 3, so minus 2 by 3 into x power minus 2 by 3 minus 1. And if you simplify, you will get it as minus 2 by 9 into 1 by x power 5 by 3. Okay. Now for inflection points. For inflection points, f double dash of x is equals to 0 or not exist, as we said. Here, see 6x exists everywhere, and that's why we are not searching for points where the second derivative does not exist. But whereas coming to this f double dash of x minus 2 by 9 into 1 by x power 5 by 3, if you observe, f double dash of x is equals to 0 won't happen. F double dash of x not exist at x is equals to 0, because denominator we have x term, right? So if x is equals to 0, f double dash of x not exist. So that x is equals to 0 may be the point of inflection, and we need to check in the neighborhood of that. Okay, minus 2 by 9 into 1 by x power minus 5 by 3. X power 5 is an odd number. So if you take positive values of x, you will get positive f double dash. If you take negative values of x, you will get negative f double dash. So x less than 0, you will get f double dash. See this, if x less than 0, this x power 5 by 3 is negative, but here we have minus 2 by 9, so f double dash is greater than 0. If x greater than 0, then here f double dash is less than 0. So in the neighborhood of 0 again, f double dash changes its sign. So for sure this 0 is the point of inflection for this graph. And now if you try to sketch the graph, in the left side of 0, second derivative is positive. So what? So what it represents? Concave upward graph. Since it is positive, concave upward. Okay, the graph may be like this. And if x greater than 0, second derivative is less than 0, that represents what? The graph is concave downward. So the graph is like this. You just try to analyze. So this is the graph of x cube and this is the graph of x power 1 by 3. Here x is equals to 0 is the point of inflection. Here again x is equals 0 is the point of inflection. Again if you sketch the tangent for this, at this particular point 0, so first derivative is infinity. So you will get a vertical tangent at this point. Again the tangent is intersecting the curve. So this is very clear that at inflection points, if you sketch the tangents for the curves, those tangents intersects the curves exact for sure. Okay. So this is about inflection point for x cube and this is about inflection point for x power 1 by 3. Now you just think about finding inflection points for x power 5 minus 5x power 4. Because of space I will erase this and then I will discuss about that. You just note down or go with a screenshot. See, for f of x is equals to x power 5 minus 5x power 4, this is first derivative 5x power 4 minus 20x cube. And this is second derivative 20x cube minus 60x square. And now I will use this space, okay, for that problem. Okay. For inflection points, f double dash of x is equals to 0 or not exist. See, when you observe this f double dash of x, for sure this f double dash of x exists always. Okay, so and that's why we need to neglect this not exist case. And this f double dash of x is equals to 0. Whenever it is 0, observe this particular polynomial or function. From there, that quantity is equals to 0 if x is equals to 0 or x is equals to 3. So finally we have 2 points. Okay, and we need to check. See, these two are usually maybe second order critical points, and I need to check at x is equals to 0 as well at x is equals to 3 also. At x is equals to 0, okay, x less than 0, x greater than 0. At x is equals to 3, we need to check x less than 3 and x greater than 3. You just observe in the left side of x. In the left side of x, since x square is positive, right? Since x square is positive, see, left side of x as well right side of x won't affect this second derivative value. Okay, left side of x as well in the right side of x. Usually in the neighborhood of x, in the sense we will take some 0.1 or minus 0.1 like that. Okay, in both the cases second derivative is negative. For x less than 0, f double dash of x less than 0. For x greater than 0, again f double dash of x is less than 0. That means f double dash of x is not changing its sign. So 0 is not point of inflection. Usually we search for point of inflections, but 0 is not point of inflection. 0 is just a second order critical point. But whereas coming to this 3, okay, if x less than 3, what will happen? If x less than 3, f double dash of x is what? Negative. If x greater than 3, f double dash of x is positive. And from this we will confirm that 3 is inflection point. Okay, so sometimes second order critical point may not become an inflection point, and this is an example for that. Have a look.